Hello and welcome back to part 2 of our lesson on heat engines. I just want to take a couple minutes to go through a couple more examples when solving these heat engine or thermodynamic process kinds of questions. So the first example here we've got a process we can see here on our PV diagram, and it goes from 1 to 2. So I might label these. I start at A, and then I move to B, and then I move to, say, step C. And the first question is it possible to have a third process which goes from C to A and completes this cycle and have that process be isothermal? So the question is, can I have these 2 points connected by an isotherm? Or could that curve be isothermal? So the thing to consider is, if that is an isotherm, if that's true, then really it's asking the question, does the temperature at C equal the temperature at A? That's really the question that's asking. Because if it is the same temperature, then yes, I can connect them with an isotherm. I don't have to. I can connect them with any other process or set of processes, but I can connect it as an isotherm. So basically we're asking, does temperature C equal temperature A? And remember that this brings us back to the ideal gas law, PV equals nRT. And so I could solve that ideal gas law for T and substitute it into this equation I've got here. So basically I've got PCVC divided by nR, which is just temperature C. And then does that equal PAVA divided by nR? Okay, and since I've got N and R on both sides, those are going to cancel out. This really, again, is one of our original precursors to the ideal gas law. If I'm at a constant temperature, then the factor P times V, the product of P and V, must be constant. They can each change, but as one goes up, the other goes down. So now if I look at my process here, so step C in my process, I can see the pressure is at 3 P naught and the volume is at V naught. So this equation here I could write as being 3 P naught times V naught. And then if I look at step A, I can see step A is at P naught, but at a volume of 3 V naught. And so this is P naught times 3 V naught. And we can see pretty clearly that, yeah, those two things are equal. So is it possible to have an isotherm connecting them? Absolutely it is, because those 2 points are at the same temperature. Now, it says, okay, suppose you complete the cycle, instead of connecting it as an isotherm, imagine we complete this cycle by adding a third process, which is isobaric. So an isobaric process from C that goes across like this, and then a process which is isovolumetric, which would stay at a constant volume, and so look like this. So basically now I'm connecting it this way, and maybe I'll label this point here D. And so the question is asking, how does the work done in this ABCD process, how does that compare to the work done in the ABCA process? So how do they compare to each other? And the answer is that the work done by ABCA will be less work done, and I should say by the gas here. It'll be a negative number, but it'll be a smaller negative number than the work done by ABCDA. And the reason is simply this, because as you recall from the previous video, the work done by a process is the enclosed area. So the total work equals the enclosed area. And you can see that if I have that ABCDA process, there's more area enclosed. Now, it's worth considering, if I start and end at A, my change in internal energy is the same, so then how is it that I'm doing more work? Well, just consider that this step right here, let's focus on process 1 is going to be the same, process 2 is going to be the same for both of these things. It's just a question, do I go from C to A or from C over to D and back to A? Well, if I follow C to A, the gas is going to do work for me as it expands. But if I follow the process from C to D, again, it's going to do work for me as it expands, but notice that the pressure is staying constant. When I go from C to A, the pressure is dropping. So I'm doing less work because I'm fighting against a smaller and smaller pressure over time. Whereas when I go C to D, I'm doing much more work because the pressure stays constant. And then I just drop back down from D to A, and I don't do any work in step D to A, but I've already done all that extra work in steps C, D. Okay, so we're gonna throw some numbers at this next one and kind of figure this one out. So in this one, I've got a cylinder with a movable piston, and it contains 0.1 moles of a monoatomic ideal gas, which all the gases are monoatomic and ideal these days. The gas initially is at a state. And it goes right. It can go through one of two cycles. So it starts at point A here, and then I can either go from A to B to C, and then follow this curved path back to A, or I go the long way around and go A to B to C to D and back to A. And so we're going to kind of compare these two things. But just note that this step CA, we haven't really seen something like this, but this is possible. It doesn't fit into one of our four categories. It's not isobaric or isovolumetric or isothermal or adiabatic. It's none of those things. It's just some other process that we haven't seen before, but any process is allowed in theory. So we got some information about it, and that is that the heat as I move from C to A is positive 685. So 685 joules flows into the system as I go from C to A. And then the work done along the path C to A is negative 120. It makes sense that it's negative because the gas is expanding. And then it also tells me that the change in internal energy between points A and B is 450 joules. Okay, so let's see if we can kind of use all that information to answer these questions. The first question is, determine the change in internal energy delta UCA. So as I go from C to A, what is the change in internal energy of the gas? Delta UCA is just going to equal the heat that flows in that step, so QCA, plus the work that is done in that step, WCA. And so a reminder, we can look at just individual parts of a process, we can look at the whole process whenever we use our first law. Well, we're given this information. We're told how much heat flows. We're told that 685 joules flows in and that 120 joules of work is done. So that means I've got 565 joules of work, and that's a positive change. And that should sort of make sense because as I move from C to A, you can see that my temperature is definitely increasing as I am increasing both pressure and volume. And so heat must have, the internal energy overall must be a positive change as we're jumping up to that higher temperature. So the question then for B is heat added or removed from the gas when the gas is taken along the process A, B, C? So we're going to kind of focus in on this process right here, A to B and B to C, okay? So is heat added or removed? Okay, and there's a couple things I want to think about here. So first of all, we should be able to kind of reason this out without even using numbers, like just kind of like picturing what's happening in this case, and then we'll throw some numbers in there just to kind of double check our work. Well, let's think about this first step. As I go from A to B, as I go from A to B, there is no work being done, right? Because the volume doesn't change, so the work AB is going to be 0. But I'm changing my state. I'm going from A to B. I'm dropping from A down to B. So I'm keeping my volume constant, but I'm decreasing the pressure, which means the internal energy must be decreasing, which means heat must be flowing out. So QAB must be some negative. I'm not going to calculate the number yet, but it must be some negative amount. Okay, and then we go over here. We go to work BC, right? So if I want to go from B to C, I can calculate the work done in this case. So the work done as I go from B to C is going to be negative P delta V. And then I'm a little squished here, but I'll plug this in. Negative. My pressure, now notice is 3, and then there's, don't forget that it's times 10 to the 5 pascals. So it's 3 times 10 to the 5 pascals. And then my change in volume is going to be from 1 to 0.75. So that's going to be negative 0.25. And just note there that that's times 10 to the negative 3. And that's getting a bit squishy. But overall, this ends up being a work which is positive because it's being done on the gas. And those negative signs cancel out, of positive 75 joules. So, but what about the heat in that step? Well, you can see here that we're doing work on the gas, and yet we're dropping from staying at a constant pressure, but we're decreasing our volume, which means our temperature must be dropping, which means our internal energy must be dropping, even though we're doing work on the gas. The only way that temperature could drop in that case is if heat flows out again in this step QBC. So you can see here that we've done a little bit of numbers, but mostly we've just reasoned out that overall heat must be flowing out of the system. So heat must be removed from the gas over that process ABC. And then of course they hit us with the follow-up question, okay, great, now calculate it. So we can throw the numbers into this and we should find that our heat overall should come out as a negative. And let's see what we get. Well, I just want to point out that let's think about what we found in this first question here. We found that as I go from C to A, I increase my internal energy by 565 joules. Well, let's think about this for a second. If I look at the total change in internal energy from A to B to C back to A, that would have to be the same as the change in internal energy from A to B to C plus the change in internal energy from C to A. I'm just kind of splitting my overall process into some smaller chunks. But if I go A, B, C, A and back again, then this whole change in internal energy also has to be 0, which is just another way of saying that the change in internal energy, A, B, C, is the negative of the change in internal energy from C to A. That's what's going to get me back to 0. So that means that this must be negative 565 joules. So the change in internal energy from, as I go from A to B to C, must be a negative change of negative 575 joules. Okay, so all that's left behind is to calculate the amount of heat. And so the heat I can find, because my change in internal energy, ABC, is going to equal heat ABC plus work ABC, which means that the heat ABC, there's too many subscripts here, is equal to the change in internal energy ABC minus the work ABC. And just a reminder that when I looked up here before, I figured out that the work done in step AB was 0 because the volume didn't change. And then the work done in step BC is just positive 75. So I could find that here by taking negative 565 and subtracting from that positive 75. And so my total answer is negative 640 joules. And you can see that because it's negative, then that means heat must have flowed out of the gas overall. Okay, question C is asking, how much work is done on the gas in the process CDA? So now it wants us to kind of go over here to this other step, and we're going to go C to D to A, okay? And so how much work is done in this process? Well, okay, think about this step here. The work in step CD is also going to equal 0 because there is no change in volume. And so really all of the work done in that process, the work done in CDA is really just the work done from D to A, because there is no work done in that first step, and that's just going to be equal to negative P delta V. And so negative, my pressure you can see is at 6, don't forget the times 10 to the 5. So 6 times 10 to the 5 pascals. My change in volume is positive 0.25, so 0.25, and again that's times 10 to the negative 3. And so the total work done is negative 150 joules. And again, this makes sense that this is negative because the gas was expanding, so work was done by the gas in that step. Okay, and so now it's asking the question, is heat added or removed from the gas when the gas is taken along the path CDA? Okay, so let's think about this a little bit more. Well, think about as we go from C to D. I've already figured out that as I go from C to D, the work done is 0, but we're going up to a higher pressure. So the only way I could increase my pressure would be if heat flowed into the system and was positive in that step. And then over here, I found that work DA, I don't even worry about the number, but I found out that it's negative. So the work was done by the gas, and yet we still expanded our volume, which means that the only way that could happen is if more heat were to flow into the system here, heat dA. So as I go from C to D to A, heat must flow into the system. So heat must be added to the gas, okay? And we can reason this out another way. Think about this. As I go from C to D to A, then the change in internal energy from C to D to A must be the same as the change in internal energy as I go from C to A. Because internal energy doesn't depend on the path, it only depends on the state, it doesn't really matter how I got there. I start at C and I end up at D. So as I go from C to D to A, it's the same change in internal energy as if I just jump from C to A. And I found early on, the first thing I found was that the change in internal energy here is some positive. So this is positive. I'm just going to keep that in mind. Well, my change in internal energy CdA is also equal to the heat CdA plus the work CdA. And we already saw that this must be positive. Great. We saw that the work was done on the gas, which is negative. So the only logical conclusion here is that the heat that flows into the gas must also be positive because the overall change in internal energy is positive and the work done was negative. Okay, that is it for part 2 of heat engines.